example where acceleration is a function of position. This problem is going to involve some Calc 2. Let me first, though, describe how we might arrive at this situation. If I have a mass on a spring, and let's say it's at rest in this position right here. If I pull the mass to the right, so I made the spring stretched out a little bit, which way is the mass being pulled?
To the left.
To the left. So if the position is positive, the net force on it is going to be to the left, or the negative direction. So if the position is positive, the force is negative. If the position is negative, so if I scrunch the spring back this way, so if the position is located to the left, then the object is being pushed back to the right. You follow that? So in the case of a mass on a spring, you're going to get a situation where the force depends on the position of the mass. If the mass is to the right, the force is to the left. If the mass is to the left, the force is to the right. If the force depends on the position, then all you do is divide by the mass to get the acceleration. So this situation, a equals negative 3x, would arise for a situation where you had a mass on a spring. I'd like to figure out what the velocity as a function of time, and position as a function of time, and acceleration as a function of time would be for this situation. So I'm given acceleration as a function of x, and I'd like to find my goal is to find velocity as a function of time, position as a function of time, and acceleration as a function of time. We already talked last class briefly on how to approach it. I showed you a little trick to make this work out. So we'll begin by using that trick, and then the rest is just a little bit of calculus. So in terms of the engineering aspect here, what we're really needing to do, we haven't even done officially up on the board, the engineering would be normally identifying the forces. Once you've identified the forces, use those forces to find the acceleration, and then once we've got the acceleration, we'll use some math to figure out these three pieces. So I've got a situation where I have an acceleration described in terms of position, and I'd like to find out these other quantities. What was the trick that I wanted to use that we had from last class? Edgardo?
You do a of x equals dv over dx times dx dt.
So a of x is always dv dt. That's what acceleration is, dv dt. And then Edgardo, you were going to now go on and say what you were going to split that up into. So dv dt, I'm going to rewrite as what?
Negative 3x dx.
Well, not yet. dv dt, you just
Oh, a of x.
Well, it is a of x. I'm going to replace this dv dt with something.
Oh, dv over dx times dx dt.
Yes. So I'll replace the derivative of velocity with respect to time, the derivative of velocity with respect to position, times the derivative of position with respect to time. And then, without looking back at your notes, what was another name for dx dt?
Velocity.
Velocity. So we had dv dx times velocity equal negative 3x. Okay? And maybe here to try to go through this we'll do the best we can in about 10 minutes or so. Let me have each of you try to fill in some of the different steps. So let me go to, I always start with Roger, it's not quite fair. Let me start with Zach. What I want to do next here, if I'm trying to solve for velocity in terms of position or something like that. Okay?
So it'd be VDV equals negative 3x dx.
Okay? And then what would I do next, Max? Yep. In order to succeed with this integral, I'm going to need to know my limits. How is this situation being started off? What are my initial conditions? So here I'll specify my initial condition is going to be, I take the spring, I stretch it 1 meter to the right, and let go. There's my initial situation. So I take this mass on the spring, pull it 1 meter to the right, and let go. If I pull it 1 meter to the right and let go, the instant I let go, that'll be where my start. What's my initial position when I first let go? I go to Vaughn. 1 meter. So my position will go from 1 to some unknown value x. Those are my limits on position. The instant I let go, which is when I start, the instant I let go, what's my velocity, Ryan? Yeah. So my velocity is going to go from 0 to v. Now those integrals, if you're looking at them, you say, that's not calc 2, that's calc 1. You're right, so far. Okay? Benson, can you do this integral right here? Good. Edgardo, the integral on the right.
That'll be negative 3/2 x squared.
Good. Evaluating from 1 to x, I guess here I'm going from 0 to v. When I put in my limits to this integral on the left, put in the v and then subtract off the 0, what do I get, Sean?
I'm sorry, I zoned out right there. What happened?
What do I get on the left side here?
Oh, 1/2 v squared.
Okay. And on the right side, Fred?
3/2 x squared minus plus 3/2 x squared. I mean 3/2.
Yeah. Good. So I put the 1 in, I just get 3x. Good. Okay, I'm going to multiply everything by 2 just to clean it up. You didn't have to do this. So I'm now going to multiply by 2. That gets rid of the half. That gets rid of that 2. That gets rid of that 2. To solve it for v, what's the last thing I need to do? Ryan, on the other side? Yeah. Yep. So I have the square root of 3 minus 3x squared is velocity. So I've got my velocity as a function of position. It's not quite what I want. I want velocity as a function of time, position as a function of time, acceleration as a function of time. I want everything in terms of time. I've now solved for velocity as a function of position. What can I do to get position as a function of time? So if I've got velocity, what can I do to get
Do
position?
v equals dx dt, and then you gotta do like a trig sub or some jazz in there. Oh man.
In a moment, right?
Eric, you got this.
And luckily, James, it's not your turn, so all you have to do is set it up. And actually, it's still Eric's okay. What should I do next?
Just trig sub it.
Well, not yet. I don't even have an integral set up
Oh,
yet. I have nothing to trick
Take
sub.
the integral both sides.
Not yet. I can't take an integral both sides unless I have all the x's on one side and all the t's on the other.
Separate it.
Okay, what should I do to separate it?
So square root of 3 minus 3x squared dx equals dt.
No. Well, tell me what I should do to this, to both sides.
Times both sides by dt.
Good? So I multiply both sides by dt. And I'm still not separated yet. What should I do finally to finish the separation?
Divide by square root of 3 minus 3x squared.
Yes. Now we will integrate both sides. what limits do I have? So Roger, you're still off the hook. Just tell me what the limits would be.
Would be for the time be from 0 to 2,
Yep.
and the hex would be from 1 to x.
Yes. Okay, because our position starts off at 1, heading up to x. I'll do the next step to clean it up a little bit. I'm going to pull the square root of 3 out of that square root. They both have a 3. So this will be dx times the square root of 3 times the square root of 1 minus x squared. And once we've pulled it out of the square root, we can pull it outside of the integral. And if I'd like, I can even multiply both sides by the square root of 3 and move it over to the other side. So I'll multiply both sides by square root of 3. So you got the integral of dx, the square root of 1 minus x squared, 1 to x, equals square root of 3 times that. Okay, now it's important to separate here. If you're stuck at this step, this is a Calc 2 problem. If you're stuck here, it's good to separate in your mind, am I stuck on the engineering or am I stuck on a math problem? So if you feel like, no, I can't do that, then the answer is I'm stuck on a Calc 2 problem. This has nothing to do with engineering. It does not reflect on your engineering skills per se. It reflects on your math skills. So let's see if together we can go through this. What we're going to try to do is be able to solve problems at the Calc 2 level. So if you see an engineering problem that involves Calc 2 type stuff, we'd like to be able to handle it. So go beyond Calc 1 type problems and be able to handle problems that have slightly trickier integrals. Imagine if we never did that, you should definitely ask at the end of your career, why did I ever learn Calc 2? So if we never needed it for some problems, you should definitely ask why we bothered in the first place. Sean, do you have a question? Or do you have a suggestion?
Yeah, is that trig identity?
Identity?
Or not identity, but
Trig subset.
Yeah.
Is it like inverse tan?
Well, instead of guessing at the answer, it's not inverse tan. Can we see what substitution I'd like to do? So for any integral, you can always choose to make a substitution. In fact, any algebra equation, you can make a substitution. Anything, you can always make a substitution. We can go through today's class by, instead of calling Roger Roger, we can call him Lampshade or something like that. We can make a substitution.
You're now lampshade.
So we can make a substitution anytime we want. Not all substitutions will make your life easier. In fact, usually the game is to try to think, what substitution can I make? That it's not that a bad substitution isn't an error; it just doesn't help you. So what substitution can I make here that will make 1 minus x squared simpler? And to help motivate that, an equation you need to know is Pythagorean theorem. Which says that cosine squared x plus sine squared x equals 1. You can derive that from Pythagorean theorem for a triangle. That's why I can relabel that Pythagorean theorem. In fact, maybe I'll do that real quick. Suppose I have a triangle, A, B, and C, where C is the longest side. Pythagorean theorem would say that A squared plus B squared equals C squared. Now, if I divide everything by C squared, C squared divided by C squared gives me a 1. This is the same thing as A divided by C parentheses squared. And that's the same as B divided by C parentheses squared. A divided by C is, if I consider this angle theta, A divided by C would be adjacent over hypotenuse, which is cosine. And then B divided by C would be opposite over hypotenuse, which would be sine. So from Pythagorean theorem, you get this relationship. Cosine squared plus sine squared equals 1. So if I see 1 minus x squared, I might think, okay, well, if I rearrange this, 1 minus sine squared x equals cosine squared x. So if you see a 1 minus x squared, it might make you think, well, if I replace x with sine of something, in fact, this is a little confusing using an x here and an x over there. Let me change all these to thetas. So if I have 1 minus x squared,